Today's session is related to the electricity, magnetism, and electrostatics paper, and Unit-1 is related to the electrostatics and dielectrics. I am Prakash, working as a lecturer in the Department of Physics and Electronics, K.B.N College. Without wasting much time, let us get into this session. In this session, we are going to see the topics that are related to electrostatics and Gauss law, and the two cases that are related to the proof of Gauss law, and what are electrostatics and introduction to electrostatics. Then we are going to see about the equipotential surfaces. Then relating to the dielectrics, we are going to see about the what is dielectrics, what is the differences between polar and non-polar dielectrics, and then we are going to see about the relation between DEP, the relation between the dielectric constant and the electric susceptibility psi. Okay, these are the topics that we are going to cover in this session. Now, coming to the electrostatics, the first topic is about the Gauss law. Now, Gauss law, it states that the total normal electric flux, which will be represented with phi e over a closed surface, is equal to the 1 by epsilon naught times the charge enclosed within the surface. Okay, it is given by the mathematical relation we can see here. Phi e is equal to surface integral E dot ds. So it is equal to the 1 by epsilon naught times q. The q is the total charge enclosed in the surface, and epsilon naught is the permittivity of free space, and phi e is the total electric flux, or we can say the total normal electric flux that is related to the closed surface, and ds represents the area vector, or infinitesimal area vector we can say. Now, there are two cases that are related to Gauss law. One, when the point source or the charge is placed within the surface. The other case is that the charge is placed outside the surface. Now we are going to see the two cases of the Gauss law. So coming to the first case, that is when the charge is placed within the surface. Okay, the charge is placed within the surface. Here we can see in this diagram that let us consider a charge plus q which is placed at a point O in an irregular surface. Okay, it is placed inside the surface at a point O. Let P be the point where the charge, okay, is to be found, or we can say the total electric flux is to find at the point P. Now the point P is at a distance of r from the charge plus q, or we can say that the point P is at a distance of small r from the point O. Let ds be the surface area around the point P, or infinitesimal surface area around the point P, and d omega is the solid angle that made by the what we can say that the distance between the point O and point P. Now we are going to see what happens in this case, that is when the when the charge is placed within the surface, that too in an irregular shaped surface. Okay, so from Coulomb's law we know that the electric field intensity is given by E is equal to 1 by 4 pi epsilon naught q by r square, where q is the charge and r is the distance between the two charges. Okay, and epsilon naught we know that the permittivity of free space. Now in this case we will see from mathematical derivations we can see that the total normal electric flux phi e over the closed surface, or we can say over the entire surface, is given by phi e is equal to q by 4 pi epsilon naught integral d omega, or we can say surface integral d omega. D omega is known as solid angle. We know that the solid angle in this case which will be equal to 4 pi. Okay, the solid angle d omega is equal to the 4 pi. here we can see that the 4 pi will get cancelled and we will left with q by epsilon naught. That we can write as the total normal electric flux is equal to the 1 by epsilon naught times the charge q, where epsilon naught is the permittivity of free space. Okay, epsilon naught is the permittivity of free space. This is how we are going to see in the first case, that is when the charge is placed within the surface. Now coming to the second case, when the charge is placed outside the surface of a closed surface which is a regular shape. Okay. We can see here at point O the charge plus q is placed. Okay. A cone of solid angle d omega made by this charge and it touches the surface at 4 places. We can see here at point P, at point Q, at point R and at point S. So the surface area at point P is ds1 and surface area at point Q is ds2 and the surface area at point R is ds3 and the surface area at point S is ds4. Now we are going to calculate the individual electric flux at that points respectively. Okay, the electric flux at point P through the surface area, we know that the surface area at point P is ds1 is given by minus q by 4 pi epsilon naught d omega, and we know that in the previous case we know that the d omega is called as the solid angle. Then the other area is q. The electric flux at q through the surface area ds2 is given by plus q by 4 pi epsilon naught d omega, and similarly the surface area ds3 at point R, the normal flux or the electric flux is given by minus q by 4 pi epsilon naught d omega, where d omega is the solid angle in this case, and the electric flux at S due to the surface area ds4 is given by plus q by 4 pi epsilon naught d omega. So when we add all this electric flux, we can see here that minus q by 4 pi epsilon naught d omega and this plus q by 4 pi epsilon d omega will get cancelled. Similarly in q and S as well. So here we can see that the total electric flux at is equal to 0. Phi E is equal to 0. In this way the Gauss law is proved in two cases, that when the charge is placed inside the surface and as well as the charge is placed outside the surface. Coming to the next topic, it is about the equipotential surfaces. Okay, what is meant by equipotential surfaces, and we are going to see how the equipotential surface are known. Okay, what is meant by equipotential surface? Equipotential surface is nothing but it is the locus of all points which have the same electric potential. Okay, the point should have the same electric potential is known as the equipotential surface. In case of uniform field where the lines of forces are straight and parallel, the equipotential surfaces are planes perpendicular to the lines of force, as you can see in this diagram. Okay, they are perpendicular to the lines of force. You can see in this diagram here, the lines of forces are straight and parallel. The equipotential surfaces are planes perpendicular to the lines of forces. Okay, as the potential difference between 2 points on the electric potential surface is 0, hence no work is in taking a charge from one point to the other point. Okay, while moving a charge from one point to other point, there is no work done. Okay. The equipotential surface are a family of concentric spheres. For a sphere of charge or a point charge, as you can see in this diagram, it is a concentric spheres, the equipotential surfaces. Now the important points in case of equipotential surfaces, you can see here the 5 points. The electric field along the equipotential surface is 0. The electric field is normal to the surface. As I said earlier, the work done in moving a charge on the equipotential surface is 0. When the charge is infinite, the equipotential surface is plane. The equipotential surface acts as a wavefront in the optics. So you can see here the equipotential surface acts as a wavefront in optics. Now we are going to the next topics that are related to dielectrics. Okay. Coming to the dielectrics, dielectrics are insulating materials that can store and transmit electrical energy. Okay. They are commonly used in capacitors and to prevent the flow of direct current while allowing alternate current to pass. Okay. Dielectric plays a crucial role in electronics and electrical engineering applications. They play a crucial role in the electrical engineering. There are two types of dielectrics. One is related to polar dielectrics, the other one is non-polar dielectrics. Polar dielectrics, nothing but they have a permanent dipole that align with an external electric field. They exhibit a positive and negative charge separation. These polar dielectrics, they exhibit positive and negative charge separation within the molecule. Whereas coming to the non-polar dielectrics do not have a permanent dipole and they do not exhibit charge separation. Unlike polar dielectrics, they do not exhibit charge separation. They are symmetric in terms of the charge distribution. These non-polar dielectrics are symmetric in terms of charge distribution. Coming to the differences between polar and non-polar dielectrics, polar dielectrics, you know that they have a permanent dipoles, while the non-polar dielectrics do not possess a permanent dipoles. Okay, polar dielectric exhibit charge separation, whereas the non-polar dielectrics do not exhibit the charge separation. Okay, polar dielectrics align with an external electric field, while the non-polar dielectrics do not show this behavior. They do not align with respect to the external electric field. So coming to the next topic, dielectric constant. So dielectric constant is represented by the letter K. It is defined as the ratio of capacitance of a condenser, which is represented by C, to the capacitance of a condenser without dielectric, is known as dielectric constant. Or you can say that K is equal to the C by C naught. Or in other terms, you can say that the dielectric constant is the ratio of permittivity of the medium to the permittivity of free space, which is given by K is equal to epsilon by epsilon naught, where K is the dielectric constant, epsilon is the permittivity of the two medium, and epsilon naught is the permittivity of free space. Coming to the electric susceptibility, which is represented by the letter Xi, the polarization vector is given by the letter P. The dielectric field is given by the letter E. The polarization vector is directly proportional to the electric field E. So P is directly proportional to E and P is equal to Xi. So where the proportionality constant Xi is known as the electric susceptibility. The Xi is given by P by E. So the electric susceptibility is defined as the ratio of polarization vector to the electric field intensity E in the dielectric. Okay. Xi is equal to P by E. By using these two definitions, we are going to establish the relation between Xi and the epsilon, or the dielectric constant and epsilon. The three important terms in dielectric terms are DEP. The first one, electric, you can see here the dielectric polarization. The induced charge per unit area is called as the dielectric displacement. Okay, the induced charge, you can see here DEP is given by D is equal to epsilon naught E plus P, where D is the dielectric displacement, epsilon naught is the permittivity of free space, and E is the electric intensity, and P is the dielectric polarization. By using this relation, we can see that we can establish a relation K is equal to 1 plus Xi by epsilon naught, where K is the dielectric constant, Xi is the electric susceptibility or dielectric susceptibility, and epsilon naught is the permittivity of free space.